So the device on your screen, the tubular looking thing, is an atmospheric condenser that I built. It has no moving parts and uses no electricity, but it only works at night during clear or semi-clear nights. So it has some advantages and some disadvantages. And I'm not aware of anything else that's been built like it, so I think it's a pretty original idea. I'm going to go over the physics of it a bit, but it just helps to see what the physical prototype looks like before we start doing that. So let me get a little closer. So the device is composed of two tubes. The inner tube here is insulated on the outside, but it's also insulated on the inside. And then down a little ways from the tube is a radiator. So that's that black thing you see. It has passages for air to travel through, but it's opaque from the top. We'll get into that later, why that is. And then there's an exterior tube here, also made out of metal. And then down below, there's another radiator. So that's another device that has passages for air to pass through, but is actually opaque. You can't see through it. And then there's insulation around the outside of this tube. And then this has nothing to do with it. This is temperature sensor. So these wires that you see on the outside, these go to different thermistors all over the device, which measure the temperature of the air at different places in the device. Okay, so let's discuss how the device operates. This device essentially works the same way that dew does. So there's some radiators inside the device which radiate energy up into space. Those radiators cool down below the temperature of the air. That cools the air, and then it cools the air below the dew point, and we get water out that way. There's two radiators in the device. There's a radiator here at the top and a radiator here at the bottom. This looks like two different radiators, but really it's one radiator that's shaped as a donut. So this is a cross section of the device, and so it looks like there's two radiators. Each radiator has channels that the air can move through. You can see that right here, that the air can move through this channel. But the channels are arranged in such a way that you can't actually see through the radiator. So if you were looking up here from the top, the radiator would look opaque, even though there's channels for the air to move through. So starting at the top, this radiator here radiates long wavelength infrared radiation to space. When it does that, it cools down below the temperature of the air, and then it cools the air around it. Then the air gets heavier, right, than the air outside, and so it falls through the radiator, right, because that air is denser. Right. The air falls through the radiator down through this column here, right? So we have this column of dense air and this column out here that's less dense. And so that dense air falls through. Then it falls through the uninsulated inner tube until we get down here. Then it comes around this corner through the second radiator, and it's cooled even further. Right? Now you have cold air rising out the top, and you have less cold air descending. So this forms a counterflow heat exchanger. Right? So the warmer air here gives up some of its heat through this metal pipe, right? And it does, because the streams are in opposite direction, that forms a counterflow heat exchanger, so that can be pretty efficient. And then finally the air leaves. So the air is coldest right here after it goes through the second radiator. So let's look at these temperatures that I measured. So I took the device outside and I measured the temperature at 6 different places. The atmospheric temperature, the temperature right above the first radiator, right? I call this radiator the motivator because it motivates the air to move through. Then the temperature right below the stack here. Then the temperature after it's gone through the counterflow heat exchanger. The temperature right after it's gone through the second radiator. And the temperature of the air right before it leaves the device. And this is what we have. Right above the temperature, right above the motivator, the first radiator, the temperature has already fallen 2.5 degrees. Then it falls through, and it's still at 4 degrees right here. Right? So it's probably actually got a little bit colder as it went through that first radiator, but it also got a little bit warmer just because this insulation here isn't perfect, and we end up at the same temperature. Then it drops another 1.5 degrees going through the counterflow heat exchanger, and then it drops another 1.5 degrees going through the second radiator, and then it warms up again on its way out of the device. So if you were going to get dew, the first place you'd get dew would be right here, right? Because this is the coldest spot, and you'd have dew forming on the second radiator, and then water would be falling off that second radiator into some sort of collection device right here. Okay. Now, one device isn't going to give you a whole lot of water. So really, the way to go is instead of having one device, you have several devices, and then you can make that outer tube maybe in the shape of a hexagon or a shape of a square, and then you can line a bunch of them up next to each other to form a kind of an array. And when you do that, the adjacent units of this array won't need radiation on the insulation on the outside because the temperature gradient, vertical temperature gradient, will be the same for adjacent units. But in the prototype, we do need insulation on the outside because there's just one unit, and we really want to isolate what's going on inside here from what's outside. Otherwise, you're going to have heat coming from the outside coming directly into this airstream here, and that's going to make the device less efficient. Okay, so let's talk about the heat flows that are involved. One is radiation, right? I'm just drawing, even though there's radiation coming off of two radiators, I'm just combining them into one arrow here in my diagram. So the radiation, you have, because of radiation, you have power leaving the device. And then you have also energy leaving the device from this airstream right here, right? This airstream carries away energy with it. So the airstream that's carrying away energy is Q convection, and I call that QC2. You also have energy entering the device from convection. That's the airstream coming in the top, right? So I call that, that's also convection, and I call that QC1. And then finally you have conduction, right? This insulation isn't perfect, so you have heat coming in through the insulation, and so that's conduction. So based on these temperatures, we can figure out what's really going on in here, right? So the first thing we'll want to figure out is what is the flow rate? That is, what is the volumetric flow rate of this air coming through here? What is that in, for example, meters per second? It's going to be really small. So one way we can figure this out is to look at the temperatures here and here, right? The heat that is flowing out of this airstream coming down, right? What that's doing is it's cooling the air. So therefore we can set the heat that's flowing out equal to the temperature difference in the energy difference between the air at the bottom and the air at the top, right? So put another way, the conduction through the exchanger wall equals the heat that is removed from the air in the cooling of that air. And this is the equation here. So we have the area of the heat exchanger, right? That would just be pi times the diameter of this pipe times the height, right? The area of that heat exchanger times the difference in temperature between the average difference in temperature between this airstream and this airstream divided by our exchanger. So our exchanger is the R value of the heat exchanger. This is, so it's like the reciprocal of the thermal conductivity. So that tells us the heat that's leaving heat that's leaving this air column, and we set that equal to the time derivative of the volumetric flow rate times the heat capacity of air times the change in temperature of the air going from there to there. Okay. And for simplicity, I just make all of these values positive. So from this formula, we can solve for the volumetric flow rate, and this is what we get. We can also solve for the speed of the air speed. To do that, we just write the volumetric flow rate as the cross-sectional area, right, pi r squared of this inner pipe here, times the airspeed, right, and that's equal to the volumetric flow rate. So we replace volumetric flow rate here with cross-sectional area times airspeed, and we solve for the airspeed. That's a little easier to visualize, so that's why I did that. It's pretty hard to visualize what a tiny fraction of a cubic meter per second means. So this is the formula we get. So the ratio of the heat exchanger area to the cross-sectional area times the ratio of these delta T's, the change in temperature across the heat exchanger wall over the change in temperature of the air, times 1 over the heat capacity of air times 1 over 2 times R film. Okay, I should have explained this. So I replaced the R of the heat exchanger with 2 times R film. So this R film is it's the thermal resistance of a thin layer of air. As it turns out, this heat exchanger wall, which is made out of metal, has negligible thermal resistance. Really what's causing the thermal resistance is these two boundary layers of air, one on either side of the wall. And so I just replaced the R value of the heat exchanger with just 2 times the R value of one air film. And you can look that up in the table and see that's the case, that the thermal conductivity of that thin piece of metal is totally negligible. Okay, and so I just solved for the airspeed. Units don't matter for these first two terms because they cancel. So I might as well do my area calculation in imperial units, since I bought all this stuff at Home Depot and it's all in imperial units. So and then the delta T's, again, doesn't really matter. In this case I did it in degrees Celsius, but you could do it in whatever. And then 1 over the volumetric heat capacity of air, which is 1300 joules per meter cubed degree Celsius, and then 1 over 2 times the R value of an air film, which is 0.044 meters squared degree Celsius over joules per second. And solving, you get 8 centimeters per second. 0.08 meters per second, 8 centimeters per second. So the air is going pretty slow. It's going like, that fast or so. And so this is why I solved for the airspeed using this kind of indirect method. It would be very difficult to solve to actually measure the airspeed directly. Like a pitot tube is just not going to work. Maybe you can find some really precise instrumentation, but I don't have access to it. So I did it this way. Now that you have the airspeed and you have the temperature of the incoming air, which is in this case negative 1.5 degrees Celsius, and the temperature of the outgoing air, which is negative 4.3 degrees Celsius. Now that you have all that, you can solve for what the net convection power is in this case. So that would be QC1 minus QC2, and that's just equal to the volumetric heat flow times the volumetric heat capacity times the difference in the temperatures. Right? And then from the energy balance, you can figure out everything else. So here's the final results. So for this particular device, on the night that I did these measurements, the Q due to convection, which we just solved for, is 7.6 watts. So there's 7.6 watts that is coming into this device due to convection, right? So that would be this minus this. Conduction is 2.4 watts, and I'll explain it in a minute how I came up with that. Radiation is minus 10 watts. So this is, there's no way to like directly measure this cheaply anyway. So I just used the formula for black body radiation, right? And that formula is just going to be this formula over here, which we're going to get to in a minute. It's just basically the transmittance, how much energy ends up actually escaping this waveguide here, times 1 minus the fractional cloud cover. Excuse me, I'm standing on the wrong side. 1 minus the fractional cloud cover times Boltzmann's constant times the emissivity of our material, which is very close to 1, times the area of the radiators times the temperature of the radiators to the 4th power, where of course T needs to be in Kelvin. So using that formula, I found out the power of radiation is 10 watts. That's 10.0 watts. It's accurate to the 10th place. And then taking the difference, you find the conduction has to be 2.4 watts. I also solved for the conduction just with formulas. I figured out what the temperature difference is between this column and the outside on average, and then I used the R value of our fiberglass insulation and the R value of the foam on the bottom, and then also the R value of the insulation on the top, and I used the differences in temperatures between these air streams and the outside to directly solve for what the conduction was, and it was really, really close to this. So whether or not you figure out the heat due to conduction experimentally, right, by taking your radiation and adding your convection to come up with your conduction, or solving for it using formulas, you get really close to the same thing. Let's note here that the radiation the power due to the radiation is negative. That's my sign convention, that if you have power leaving, you make it negative. So that way all of these sum to 0. So we now know what's going on in this device outside on a cold night here where I live in Albuquerque, which is in the desert, and we're in the wintertime. So this is the worst possible really climate and time of year to try this device out, because you're not going to get any water. So there's a very relevant question here, which is how much water would you get if you took this device and you put it in a different climate? And so I wrote a computer program that answers that question, I think relatively satisfactorily. So I'm going to show you how I did that. So first we need to define a few variables. So first of all, define delta TA as the temperature of the atmosphere minus the low temperature of the air. So that would be, in this case, the difference between my atmospheric temperature and 7 degrees, right? So 5.5 degrees in this case. And this is, again, keeping with my usual way of doing things. I'm just going to make this positive, just for simplification. So that's why T atmosphere is first. T atmosphere minus T out, that's going to be the temperature of the air coming in minus the temperature of the air going out. I'm going to set that equal to, or that's equal to 1 minus E times delta TA. So what is E? E is kind of like a system-wide efficiency, right? So in this case, it's the heat exchanger efficiency times the fraction of the cooling that occurs at the bottom of the device, right? So the more cooling that occurs at the bottom of the device, the more efficient your heat exchanger is, right? Because there's more heat that can come from this airstream coming down into the airstream going up. If all your cooling occurs up here, of course you're not going to get any of that cooling back. So that's why it's defined this way. And then of course if the efficiency is perfect, right, then you're going to have the same, then this side of the equation is going to be 0 and you're going to have the same temperature going out that you have coming in, which obviously that's not going to happen. But that's just to sort of show that that formula makes sense. I define MW as the mass of the water that's extracted, and SC is the fractional cloud cover above the device. So if half the sky is covered with clouds, then my assumption is that that's going to mean that half the radiation it's not that half the radiation leaves the device, it's that the same amount of radiation leaves the device, but then half of the radiation that leaves the device actually gets radiated back onto the device by the clouds up above. It's actually going to be a little bit less because clouds are colder because they're higher up. But, you know, so I'm actually being a little bit conservative there, which we'll see. Okay, epsilon is the emissivity, tau is the transmission coefficient. That's, you know, what percentage of the infrared radiation that's radiated by the radiator actually escapes out the top of the waveguide, these reflecting pipes. That's a really, really high number. Experimentally, I've determined it's just super high, so it really doesn't affect it very much. And then you also from data in the literature, I found out that you know, like steel like this is just super reflective for long wavelength radiation. T is the radiator temperature. U total is the total thermal conductivity of this this entire device. Right? So now we do our summation of heat flows. Right? So we have into the device we have QU, which is our conduction. Right? Also into our device QC1. Out of the device is QC2. It's this one. Convection leaving, and then finally P of radiation. Then we replace these terms with formulas, so QU becomes U total times T, delta TA. QC1, right, this is the, this term here, these two terms here get combined. So we have the total amount of energy gained from convection is the heat capacity of air times the flow rate of air times 1 minus the efficiency times delta TA. So that just comes from thermodynamics. And then our radiation term is minus the transmittance times 1 minus the cloud cover times Boltzmann's constant times the emissivity times the area of the radiators times T to the fourth. Now I make a substitution. You notice in this equation there's no mass of water extracted, so I have to get that somehow. So what I do is I replace the volumetric rate of flow with two terms. So the first one is I replace delta V over delta T. I replace that with delta M delta T times delta V delta M. Okay, so now I have delta M in the equation. And then this whole equation, right, gets set equal to this term here. This term here is the latent heat of vaporization times the rate at which water is extracted from the air. So that's delta M of water over delta T. So notice I didn't set it equal to 0, right? Previously, when I wasn't extracting water, right, I could say, you know, this plus this minus, you know, minus this equals 0. But in this case, I actually don't have that energy balance because I have excess energy is leaving the device, and that's what I'm using to condense the water. So this won't be in balance on the left side of this equation. It's going to be equal to some negative term because I have more energy leaving than entering. And that energy that's leaving, the excess energy that's leaving, is used to cause this phase change. And that's the latent heat of vaporization of water times the mass flow rate, the change in the amount of mass of water you're extracting over the amount of time that it takes to extract that. And it's negative, right, to keep our signs consistent. Okay, so now I solve for delta MW. That's really what I'm interested in, how much mass of water I can extract in a given period of time, and I get this. So let's talk about this equation for a minute. So delta MW, this is the amount of water that we extract from the air over the course of the period of time delta T. It's going to be in kilograms if all of this is in standard units, and it's proportional to, first of all, the area of our array of condensers, and that should make sense, right? If we double the area of our condensers, we should double the amount of water that we're able to extract. It's also proportional to delta T. That makes sense also because if we double the amount of time that the condensers are operating, we'll also double the amount of water we get. On the top of this fraction here, we have this first term. This is the amount of energy that leaves the device because of the radiation of the radiators. And then we subtract the second term here, which is this is the amount of energy that enters the device through conduction. So hopefully that should make sense. This is the amount of energy we have to work with. The amount of energy that leaves through radiation minus the amount of energy that enters through conduction. On the bottom of the fraction, we have the latent heat of vaporization of water, right? So this should make sense because the larger the latent heat of vaporization, the more energy it takes to extract that water, the less water we'll get, right? So larger LW means smaller MW. And then this term right here, this term is the most difficult to understand. So delta TA, the larger that term is, the smaller MW is. That was what we would expect. It takes energy to cool air, so the more we cool that air, the less water we get. The lower the efficiency is, right, the less water we get. Heat capacity, obviously the larger the heat capacity of the air, the less water we're going to get because it takes more energy to cool that air. And then we have this term right here, delta MW over delta V. So what is that? What that is the change in the density of water in the air as the air is cooled. So let's talk a little bit about that concretely to make that a little more clear what that is. So here we have some data from Cairo, Egypt. This is in July, and in July the dew point at night, this is 20 degrees Celsius. So if we cool the air from 25, which is the atmospheric temperature, to 20, we're not going to get any water out, right? Because we haven't gone past the dew point. So delta TA in that case is 5 degrees. We've dropped it from 25 to 20. And the density of the air at that point, the density of water at that point is 0.01732 kilograms per meter cubed. That's how much water is in the air at that point, and we're at 100% relative humidity because we're at the dew point. Now if we drop that air 5 degrees, delta TA is then 10 degrees because we've dropped from 25 to 15. We have less water in the air than we had before because we're 5 degrees below the dew point. That means some water has condensed out. The difference between these two densities is 0.00446. That's the change in the density of the water. That is delta MW over delta V, what we have right here. Now as we drop the air even further in temperature, right, say down to, let's say 10 degrees, our delta TA is 15 because we've dropped from 25 to 10. And now we have an even larger difference in these densities, right, 0.00789. So if this number is large, delta MW over delta V, the reciprocal is small, right, which makes this term smaller, which means that delta MW is larger. That makes more sense. If we have a larger change in the density of the water in the air, then we've extracted more water out. So this whole formula here should hopefully make some sense. Now, rather than do a calculation with all the numbers and all of the units, I don't really have space on this board and this video is already long enough. I'm going to show you a computer program I wrote that does this automatically. So one thing before I show you the computer program that we should note is that this doesn't actually give you one number for delta MW. It's going to give you a different number depending upon how much you drop that air temperature. Put another way, the further you drop that air temperature, the lower the airspeed is going to be in here, and the lower the volumetric the volumetric flow rate, right? The lower the volumetric flow rate, the lower the airspeed. That means the air that does go through here is going to be cooled more. So you're not going to get a single number. You're rather going to get your the water that you extract is going to be a function of the airspeed or a function of the volumetric flow rate, or put another way, a function of delta TA. And so the computer program I wrote actually gives you a range of delta MWs as a function of delta TAs. And then you can see, okay, this is the most efficient temperature that we can drop the air to. Right? This is the computer program I wrote to model the performance of the condenser in a humid climate. I wrote the program in Python. You can see the condenser variables right here. In this case, I've set the radiator area to 100. So this would be an array of devices 10 feet by 10 feet. The emissivity to 0.97. This is a very reasonable value for emissivity, both based on experiments that I've done and also just from looking at figures for opaque materials in the long wavelength infrared radiation range. The back thickness is 2 inches, so this is the thickness of the insulation on the back, like on the underside of the device or array of devices. This is actually less insulation than I have in my prototype. The R value of that insulation per inch. The radiator temperature drop is defined as the lowest temperature of the air in the device minus the temperature of the radiator. So it's how many degrees below the lowest air temperature the radiator sits at. The lower this number, the more efficient the device is going to be, because it means the radiator more efficiently cools the air around it, and so it can radiate at a higher temperature and therefore radiate more radiation. But the program isn't particularly sensitive to this parameter. The motivator factor, this is the fraction of the cooling in the device which occurs at that upper radiator, which I've previously called the motivator. So the lower this number is, the more efficient the device will be, because it means that more cooling occurs at that lower radiator, and that means that the heat exchanger is able to extract more heat from the incoming airstream. The transmittance, in this case I set to 0.95. That is the fraction of the energy emitted by the radiator which exits the metal pipes. Put another way, with a transmittance of 0.95, 5% of the radiation that's radiated by the radiators will be absorbed by the pipe. And that's a low number, and it should be. In this case, you do have very high transmittance. That's verified by experiment, and also by numbers in the literature. In this case, I'm setting the airspeed. Let's set the airspeed to 0.08, which is what we came up with when we looked at my physical prototype. I'm setting the air exchanger efficiency, in this case, to 0.5, just being pretty conservative. We can go back and change some of these figures in a bit. Now we're going to input the atmospheric data. I'm going to choose Chennai, India. So this is an area in India, Southeast India, where they're running out of rainfall, but in the dry season they have 12 hours of darkness and they have high relative humidity. So it's a perfect place for this device to work. In this case, the lowest rainfall is in March, and in March the cloud cover is 0.27. There's 12 hours of darkness. It's 26 degrees on average at night, and the dew point is only 2 degrees lower than that. So this is really, really ideal atmospheric conditions. So I set the variables to those values. Next come the constants. We have the heat capacity of air, the latent heat of vaporization, and the latent heat of fusion of water. Now in this case, we're running the device in a very warm climate, so we're only going to need the latent heat of vaporization. But if you were running the device in a cold climate, not only would you have to condense the vapor into water, you then also have to freeze the water into ice, and then you'd have ice accumulating on your radiators, and then in the morning, sometime during the day when it gets hotter, that frost would melt. And that's actually not a problem because the emissivity of ice is actually pretty darn high. But we're not going to worry about that. The computer program that I wrote will take into account the latent heat of fusion if the air temperature drops too far. That is below freezing. Boltzmann's constant, then we have these positive and negative density lists. This is the density of water in grams per cubic meter at 0 degrees. And then here it is at 1 degrees, like 1 degree, 2 degrees, 3 degrees. So you can see these numbers are increasing as we increase the temperature of the air, and then this is an equivalent list at 0 degrees, -1 degrees, -2 degrees, -3 degrees. So you can see that the maximum water density decreases as the temperature goes down. This is at 100% relative humidity, both of these lists. Okay, so the program basically iterates through these lists and then tells you how much water you would expect at a given low air temperature. So let's do that. Let's run the program. So here we go. So at 23 degrees here, we would get 5.27 gallons. At 22 degrees, we'd get 6.15 gallons. At 21 degrees, we'd get 6.42 gallons. Now, the number of gallons we get is a function of our low air temp, but it's also a function of airspeed. But airspeed and low air temp are not independent of each other, right? To get a particular low air temperature, you would send that air through at a particular airspeed. So we have many airspeeds here, but you'll notice at the beginning, we set our airspeed. We set our airspeed to 0.08. So the program is assuming a particular airspeed. So the only prediction here that's actually valid is going to be this first one, right? Because it's close to 0.08 meters per second, 8 centimeters per second. If we wanted to drop the temperature lower, we'd actually need to input a lower airspeed. So let's do that. We'll put in an airspeed of 0.05. And now the program says that at an airspeed of 0.05, we get 6.15 gallons. And we can drop that a little lower. 0.04. Okay, so we're looking at a little over 6 gallons, it looks like, given the current parameters that I input to the program. Now, a good question might be, how do you change the airspeed? How do you vary that? Well, one method might be to increase or decrease the stack height below your motivator. You could also put a choke in to try to slow that airspeed down, but of course that would only slow the airspeed. It wouldn't be able to speed the air up. Let's see what happens if we make the device somewhat more efficient. So let's change the motivator factor to 0.3, and let's change the heat exchanger efficiency to 0.66. So we've made the heat exchanger taller and thinner, or we've added some fins. We've just done something to make it a little more efficient. Now we can see that the number of gallons that we collect has gone up. So we're still at an airspeed, we're at an airspeed of 0.04, so now we're getting 7.17 gallons. So with a less efficient device, we were getting a little over 6 gallons. With a more efficient device, we're getting a little over 7 gallons. So that's with a 10 by 10 foot condenser array. So with 1,000 square feet, you'd be looking at 71, 72 gallons with the more efficient device. And that's really the top line result.